Chale ji, Bismillahirrahmanirrahim. Let us start the class. And this is our 7th lecture. And today we will start with the clamper circuits. In the previous classes, we have done the diode applications and rectification using a single diode, rectification using 2 diodes, and rectification using 4 diodes. After that, we did the clipper circuits, and inshallah this time we will start with the clamper circuits. So this is article number 2.9, clampers. First we will have a look at the definition of clampers, and then we will see the circuit and the working of the clamper circuit. So by definition, a clamper is a network constructed of a diode, a resistor, and a capacitor that shifts a waveform to a different DC level without changing the appearance of the applied signal. A clamper is a network constructed of a diode, a resistor, and a capacitor that shifts a waveform to a different DC level without changing the appearance of the applied signal. So in a clamper, we will not change the wave shape of the signal. Rather, we will just change the DC level in the signal. So if the input signal is AC, then we will add a small amount of DC, or we can add a certain amount of DC. And if there is already a DC inside the AC, then an additional DC will be added. So as an explanation, additional shifts can also be obtained by introducing a DC power supply to the basic structure. And this we will see in a later slide. This is a very basic clamper circuit. It consists of input terminals. Here VI represents the input terminals. Then we have a capacitor C. This capacitor by its symbol is an electrolytic capacitor. Then we have a diode, and for this circuit shown, the anode terminal of the diode is connected to the positive terminal of the output, and the cathode terminal of the diode is connected to the ground. And the output voltage is taken across the anode and the cathode of our diode. Then in parallel to the diode is the resistor. It can be our load resistor also. So R represents the load resistor. Now let us read the description. Clamping networks have a capacitor connected directly from input to output with a resistive element in parallel with the output signal. The diode is also in parallel with the output signal, but may or may not have a series DC supply as an added element. So in figure 2.89, we see a very basic clamper circuit that does not show a external series DC power supply. But in later slide, we will see that we will have a DC power supply connected in series with the diode, and that will also be a clamper circuit. Okay, now we come to the next slide. So in this slide, we will start to learn how to analyze a clamper circuit. There are a certain amount of steps that are to be followed, and these steps should be followed in the sequence shown. So the step number one is start the analysis by examining the response of the portion of the input signal that will forward bias the diode. That is, we will start the analysis by looking at the portion of the input signal that will cause the diode to be forward biased. Let us look at the input voltage. Let us look at the clamper circuit. The input voltage from 0 to T/2 has a positive portion or a positive half. Then the same input voltage from time T/2 to time T has a negative portion or a negative part. We will start to analyze the clamper circuit with first considering that portion of the input wave that will forward bias the diode. So let us look at the clamper circuit. The clamper circuit is similar as we saw in figure 2.89. Here in the input terminal, we will apply the input. Then we have the capacitor and the diode. So now let us just stop over here and let us examine the circuit, and let us examine that what will be the direction of the polarity, or what will be the direction of the voltage, so that it causes the diode to be forward biased like the arrow shown. This will be possible only when our first terminal, we call this terminal A, when terminal A is at a positive polarity, and let us call the other terminal number B, when terminal number B is at negative polarity. So when A is at a positive polarity and when B is at a negative polarity, only then the diode will be forward biased. So up till here we have done step number 1. Now we are proceeding to step number 2. Step number 2 is during the period that the diode is in the on state, assume that the capacitor will charge up instantaneously to a voltage level determined by the surrounding network. Step number 2 is a very important step. It describes that once we have decided which polarity of the input waveform will forward bias the diode, then the second step is that we will assume that our capacitor C, it will charge in a very small time. The capacitor will charge in a very small amount of time, and the capacitor will charge to a voltage level as determined by the surrounding network. Now, what does this line mean? So let us look at figure number 2.89. What we have is we have a input voltage across terminal A and terminal B. Then we have a capacitor C and a diode connected as shown, with terminal A at a positive potential and terminal B at a negative potential. The diode will be forward biased, and this will happen from time 0 to time t/2. When we apply this part of the waveform, the capacitor will instantaneously charge up to the voltage level. Now, what will be the value of this voltage level? If the input voltage is V, then the forward biased diode, it will either have 0 volt if we are considering ideal diode, or if we are considering a practical diode, then the voltage drop will be 0.7 volt in case of silicon when the same diode is forward biased. Therefore, voltage of the capacitor will charge to a voltage either input equal to V if we are considering ideal voltage, if we are considering ideal diode, or if we are considering a practical diode, then the capacitor voltage will become V minus 0.7 volts. And this capacitor, not only will it charge to a voltage equal to V or V minus 0.7 volt, it will also charge up in a very small amount of time. Now let us examine the output waveform from time 0 to t/2. The output waveform is 0 volts from 0 to t/2. This is due to the fact that we are using a ideal diode, and secondly, the diode is forward biased from 0 to t/2. Hence, output V out is equal to 0 volts from time 0 to t/2. And if we want to have a equivalent circuit look at the time 0 to t/2 when the diode is forward biased and the capacitor is charging, then we will look at figure number 2.90, where we see the DC power supply. Now this DC power supply only represents the part of the input signal from time 0 to t/2, where input voltage is positive at one side of the capacitor and 0 volt at the ground. So this makes it a positive polarity. The capacitor is charged and a current is flowing and the diode is forward bias represented by a short circuit. Therefore, the output voltage from time 0 to time t by 2 is 0 volt. Therefore, in the output voltage waveform, we draw 0 volt from time 0 to t by 2. Now, why did we say that the capacitor charges instantaneously? Why are we saying that capacitor will charge up instantaneously? The answer is that if we look at the circuit consisting of the DC power supply, the capacitor C, and the forward bias diode, we see that the capacitor has no resistance in series. Therefore, the time constant, which is equal to 5 times RC, the time constant, which is a multiple of resistance and capacitor, it gives us the time required to charge the capacitor. Here in this part of the circuit, the resistance is almost zero. Therefore, the time will be zero or almost zero. That means the capacitor will charge up instantaneously. Now let us come to the step number 3. Step number 3 states that assume that during the period when the diode is in the off state, the capacitor holds on to its established voltage level. That is now we are discussing time t by 2. So in step number 3, we are assuming that the waveform has now entered the negative part. And if we look at figure 2.91, the polarity has been reversed because from time t by 2 to time t, the polarity of the input power supply is now negative. Therefore, now the capacitor and the power supply are both acting in series, and the voltage available across the output is equal to minus V in minus Vc. And if we look at our previous equation, Vc is almost equal to V input. Therefore, output voltage is equal to minus twice of the input voltage. Twice of the input voltage. So if you look at our figure 2.92, from time t by 2 to time t, the output voltage will be minus twice of the input voltage. This will happen from time t by 2 to time t. And we can always argue that why this output voltage is straight, whereas we see a resistor. The resistor will eventually consume the energy of the capacitor. However, the answer is that we are taking a resistor of quite a large value. Therefore, output voltage waveform looks straight, and in fact it will remain straight.
Kindly repeat the step number 2.
In step number 2, terminal A is at positive potential, terminal B is at negative potential. Therefore, the diode is forward biased and the capacitor is now charging. And since the capacitor has no resistance in series, this resistance R is in parallel with the short circuit. So the capacitor will only look at the short circuit. And the capacitor has no resistance, therefore the capacitor charges instantaneously. And our capacitor C will charge to a value equal to the input voltage. Okay, so now let us come to the next slide. The next slide is example 2.22, and the statement of the example is determine V out for the network of figure 2.93 for the input indicated. In this example, we have to find the output voltage waveform for the circuit shown. Let us first examine the input voltage waveform. The input voltage waveform from time 0 to time t1, it has a voltage of 10 volts from time 0 to time t1. Then from time t1 to time t2, the input voltage is minus 20. And from 0 to time t2, we have one complete cycle. And the second cycle, starting from time t2 to time t4, is of identical nature. So we will examine the performance of the circuit from time 0 to time t2. This was the examination of the input waveform, and we are examining this voltage waveform because of step number 1. Secondly, let us look at figure 2.93, the circuit diagram. The circuit diagram has an input terminal. We will label the input terminal as A and B. So input terminal consists of terminals A and B. Then we have a capacitor. The capacitor value is 1 microfarad. And then we have a diode. The diode, it is not specified either the diode is silicon or germanium. So we will consider the diode to be ideal. Then in series with the diode, we see an external DC power supply of 5 volts. This power supply is a DC power supply connected in series with the diode, and this series power supply is external. It does not represent the barrier potential of the diode. It is an external power supply of value 5 volts. Then let us label the cathode terminal of the diode as terminal number C, and then we have this minus input negative terminal of the battery same as terminal number B, and then across the output is a resistor of value 100 kilo ohms, and output voltage Vout is taken across terminals C and B. And another thing to note is that the frequency of the input signal is 1000 Hertz. So what we have to do is we have to determine the output voltage waveform. And this figure shows a clamper circuit with an additional DC power supply. So this was step number 1. In step number 2, we will consider that portion of the input waveform which will forward bias the diode. So which part of the input signal should we start with? Should we start from 0 to T1 or should we start from T1 to T2? If we start from 0 to T1, then it will cause the diode to be reverse biased. So we should not start our analysis from time 0 to T1. In fact, we should start our analysis from time T1 to T2, because from time T1 to T2, terminal A becomes negative and terminal B becomes positive. With this arrangement, our diode will be forward biased and a current will start to flow, and a current will start to flow like this. Okay, so we are going to start from time to T2. From time T1 to T2, what we have is we have the voltage power supply connected like this. This is positive and this is negative. And the amplitude is 20 volts. And the amplitude is 20 volts. And our diode is now forward biased. The diode is now forward biased. So with the diode forward biased, the capacitor will now charge. And the capacitor will charge to a certain value. And this capacitor will charge instantaneously. So first of all, what is the value of voltage across capacitor from time T1 to time T2? Remember that now we see two power supplies connected in series, the 20 volt from VAB and the 5 volt of the external DC power supply. So 20 plus 5 is equal to 25 volts. Therefore, when this 25 volt is applied across the diode in the capacitor, assuming ideal diode, the capacitor will charge to a value equal to 25 volt as shown. So now capacitor voltage is 25 volts. And then what is the output voltage across terminals C and B, or across the output Vout from time T1 to T2? Remember that the diode is forward biased. Therefore, if we look at figure 2.94 over here, this circuit shows the equivalent circuit when the diode is forward biased and the diode is represented by a short circuit. Therefore, the output voltage from time T1 to T2 is 5 volts. So if we draw the output voltage on the graph Vout, this graph on the right hand side shows the output voltage waveform from time t1 to t2 is only 5 volts, and up to time t2 the capacitor has now been charged, and we can look at the polarity of the voltage across the capacitor like this, and this is due to the current direction. So this was the analysis from time t1 to t2 when the diode was forward biased. Now we come to the remaining part when the diode is reverse biased. When the diode is reverse biased, what we have is that is from time t2 to time t3. We have a voltage that is now reversed. Therefore, the 20 volt is represented by a battery with polarity such that terminal A is connected to the positive part and terminal B is connected to the negative part, and the magnitude of the battery is only 10 volts due to this part or due to this part. So the capacitor was charged to 25 volts. And now we have a DC battery of 10 volts across A and B. Now let us look at the terminal number C, or the negative part. Let us look at figure number 2.95. We have a DC power supply of 10 volts connected as the input and a charged capacitor of 25 volts. So node number C is at how much voltage? The node number C is at 35 volts, and this is positive. This is positive over here. The diode which was connected over here, it has the cathode at positive 35 volt and the anode at 5 volt. Therefore, this diode is reverse biased and it will not conduct any current, and it is represented as a open circuit. So now what will happen? The diode will not conduct, and the output voltage is equal to 10 volts plus 25 volts, and this output voltage is equal to 35 volts from time t2 to time t3. Thus, in the output voltage waveform, we see that the output voltage increases from 5 volts to 35 volt, and it remains 35 volt from time t2 to time t3. After time t3, we will enter the negative part where the diode becomes forward biased and output voltage becomes 5 volts only. So this was the step number 2 and 3 of the example. Now, in addition, let us look at the time constant, because we see a resistor of 100 kilo ohms also connected across the load. This introduces the concept of the time constant, which is equal to T is equal to RC, and the time constant is equal to the value of the resistance multiplied by 0.01 microfarad, which is 10 milliseconds. So the time constant of this circuit is 10 milliseconds. And we know that from network analysis, the capacitor charged to its maximum value in 5 time constants, the capacitor will charge to its maximum voltage level. In the network analysis, we have seen that the capacitor will either charge or discharge in a time of 5 time constant or 5 multiples of time constant. Therefore, the last line says that the total discharge time is therefore 5 time constants, which is equal to 50 milliseconds. So if we just summarize this example, let us compare the input voltage waveform with the output voltage waveform. The clamper circuit did not alter the wave shape. The input voltage waveform was a square wave. The output also remains as a square wave. However, what the clamper circuit did was that it introduced a DC level, and this DC level is of 5 volts over here. This is the introduction of 5 volt DC level brought by the help of the clamper circuit. So it has in fact level shifted the input voltage. If we do not use a 5 volt input voltage, then the level shifting will be 0 volt and the square wave will entirely occur in the positive part. Whereas if we look at the input waveform, the input voltage waveform operates in the positive part and also operates in the negative part. So this was the analysis. Example number 2.2. So now we are coming to the next slide. This is example number 2.23, and the statement is that repeat example number 2.2 using a silicon diode where Vk is equal to 0.7 volt, or the barrier potential of the diode this time, assuming a silicon diode, is that the barrier potential is 0.7 volt. So we will start again from time. The wave shape, the input voltage wave shape is the same. It has 0 to 10 volt from time 0 to T1. Then from time T1 to T2, the input voltage is minus 20 volts. The remaining circuit, in addition, there is a change in the capacitor. Capacitor is equal to 1 microfarad this time. The diode is of silicon value, and input voltage and the external DC voltage is 5 volts. We will start our analysis from time T1 to time T2, where the input voltage is reversed and we have a minus 20 volt available across the input. This minus 20 volt will forward bias the diode, and we are now taking into consideration the voltage drop. Therefore, from time T1 to T2, the output voltage is 5 volts minus 0.7 volt, which is equal to 4.3 volts, 4.3 volts. And output voltage waveform is 4.3 volt from time T1 to T2. Then in the same time from T1 to T2, the capacitor is also charging. The capacitor will now charge to a value of 20 plus 4.3, that is 24.3 volts. So this will happen from time T1 to T2. Then from time T2 to T3, the diode will become reverse biased, and the input voltage waveform will be plus. This plus 10 volt will occur in series with 24.3 volt of the capacitor. Therefore, output voltage waveform, that is from T2 to time T3, is only equal to 34.3 volts. Again, we see that there is a level shift of 4.3 volts in the output voltage waveform. Now we come to the next slide, and the title of the slide is Clamping Network with a Sinusoidal Input. Clamping network with a sinusoidal input. The input voltage waveform in this case is a sine wave, such that the peak voltage is 20 volt and the peak to peak is 40 volt, and the nature of the input voltage is a sine wave. The network that we are using, the clamping network that we are using a capacitor, we are using a diode and a DC power supply. If you look closely to the circuit, the DC power supply is connected such that the positive terminal of the DC battery is connected to the ground, whereas the negative terminal of the battery is connected to the anode terminal of our diode, and the cathode terminal of the diode is connected to one plate of the capacitor, and it represents our output voltage. So if we label them, VA and VB represent the input terminals, and this node represents the output terminal. So how should we analyze this circuit?
Sir, first we will check for which part of the wave the diode is forward biased.
So if we look at the input voltage waveform, it is a sine wave which has a positive half and a negative half. And if we use the positive half first, where A is positive and B is negative, such that it is 20 volt, we are taking the extreme. So will it forward bias the diode or will it reverse bias the diode?
Reverse biased.
So it will reverse bias the diode.
Bias.
Yes, it will reverse bias the diode. So we should not start from the positive portion. Rather, we should start from the negative portion of the input voltage, where input voltage reverses in polarity and terminal A becomes negative, terminal B becomes positive, and this voltage, let us take to be 20 volts. This 20 volt will now act in series with the 10 volt, but the 10 volt is connected oppositely. So what is the voltage at, let us take this node and call it node number D. What is VD? Assuming that the input voltage is at peak over here. This is the peak value. What is VD? VD is equal to 20 volt from the input power supply minus 10 volt of the DC power supply. That is equal to 10 volts. That is equal to 10 volts. Thus, the diode is now forward biased, and VD is the voltage available to the diode and the capacitor. The diode is now forward biased, and the voltage drop of the diode can be considered, or let us take an ideal case. Let us take an ideal case. What will be voltage VCA? VCA. What will be voltage VCA? Looking at this figure, the voltage VCA will also be 10 volts because diode is forward biased. So voltage VCA is 10 volts.
Sir, why are we not taking the output voltage when diode is reverse biased?
In fact, we will take that case in the next step. But in this step, we will look at the circuit and we will look at the input voltage waveform, which will cause the capacitor to charge. And it will charge, the capacitor will charge in the negative half of the input voltage waveform. Therefore, our capacitor has now a voltage of 10 volts.
Sir, capacitor can charge in positive half of the cycle.
Capacitor will charge during the negative part of the cycle.
Sir, when diode is reverse biased, the resistor and capacitor.
No. When the diode is forward biased, only then our capacitor will charge, like the arrow shown. And this arrow will, and this direction of the arrow will happen only in the negative part. Yes, you can argue that we have a resistor in series. We must not forget that this resistor is a load, and it has a very, very large value. So at this time of analysis, we are ignoring the resistor and we are considering the capacitor, the diode, and the DC power supply. So the capacitor now charges to a voltage of 10 volts. And corresponding to the input voltage, our output voltage will follow a sine wave with a value of minus 10 volts. Our capacitor is now charged. Therefore, in the positive part of the input voltage, the capacitor is charged like this with a value of 10 volts. And now this time, during the positive part, what we have is we have a 20 volt such that terminal A is positive and terminal B is negative, and 20 volts over here. So this 20 volt will add with the 10 volt of the capacitor such that the output voltage will be positive 30 volt. Thus, the output voltage waveform will follow a sine wave and the peak value is 30 volts. And as a summary, the output voltage waveform is the same sine wave but with a certain amount of DC level shifting, and it is level shifted by 10 volts. Right, so now we come to the next slide.
सर सेकंड वेवफॉर्म में -10 वोल्ट के बारे में बता दें या किस तरह है.
So now I'm going to answer why we have a -10 volt in the negative part. And this happened when the input voltage waveform was -20, or when terminal A was negative and terminal B was positive. During this time, the diode was forward biased. And with the forward biased diode, when we represent the diode by a short circuit, the voltage appearing across terminal V, C, and B, which is also equal to our output voltage. This is equal to -10 volts. So this external DC value represents the level shifting of the output signal. And this -10 volt, it is here because of this DC value. ठीक है?
Yes sir.
Okay, so now let us come to the next slide. The next slide consists of a variety of clamper networks with DC power supply or without DC power supply. And this figure 2.100 is left to the students, that they will understand the circuits, analyze the circuits, and understand how input voltage is altered by the clamper net and how a certain amount of DC is added. So I will expect the students to analyze all of the 6 circuits shown.
Sir, what is the input voltage of second circuit?
The input
The
is the
same
same. The input
square wave.
The input for all cases, for all 6 cases, is a square wave. And to analyze this, the input for all 6 diagrams will be square wave, and all the students will analyze them using ideal diodes. And for your convenience, what I can write over here is that we can assume that V is larger than V1, because we see V1 in 4 cases. We can take V1 smaller than V in, or we can also take V equal to V1. And then in the last part of the analysis, you can consider V to be smaller than V1. So we will take, in the first case, V larger than V1. In the second case, we will take V equal to V1. And in the third case, we will take V smaller than V1. And then analyze all the circuits.